Good afternoon. Hey! I'm always amazed by how many people turn up for these talks at this kind of conference. Last year, the same conference, I talked about the philosophy of software architecture. And I thought, it's a dev conference, so it's going to be me and 4 old people in a little room somewhere talking about Aristotle. And then everyone turned up. I was like, uh-oh. Same thing's happening today. Uh-oh. So I know we've been listening to the talks, listening to the buzz in the air. There's a lot of excitement about this Gen AI thing. What is this? What's it going to do? What's the future of programming? What's the future of development work? There's a lot of wild speculation, hype, nonsense, and some fear. And now, for the next hour, we're going to get a break from that specific type of fear and talk about a different one. Hey. What's the future of architecture going to look like with everything? Everything feels like it's moving. Everything's changing. Nothing's staying the same, except for the architects who are still drawing lines and boxes. What's going to become of us? Is there going to be something else that draws our lines and boxes for us? So if you haven't met me before, I'm actually based in Sweden. Boo. I run a little company called Black Tulip Technology. We work all over the world with architecture, research, project rescue, and education. I'm just finishing off a PhD. I think I said that last year as well. I'm just finishing it off. But if my professor's watching this on YouTube, I mean it this time. Finishing off a PhD in complexity science and software engineering. And this journey towards this PhD, which I've taken quite late, after a 25-year career in the industry, I decided to go and get a doctorate. And this experience has changed the way I look at architecture, it's changed the way I looked at everything. And so if we go back in time, 7 or 8 years, after I left a large company that I used to work for, I started to do this kind of thing. I started to talk on stages and talk about my ideas. And I had this very particular way of looking at architecture that was very, very different than what other people had done before. And I got up on stages like this and I said, look, gang, I have all these ideas and I think things work like this, and I think it'll be better if we did this. And I was very excited about my ideas. And what happened was the people in the audience, they just nodded and they went, yeah, that sounds really good. And I thought, no, wait a minute, that was too easy. Why did you just believe me? I could say anything. And you'd all just go, yeah, that sounds good, we'll do that. Right? That's how we got microservices. and it's just too easy to do this. And I thought, no, I want to have a bit more rigor. I want to have a bit more meat on the bone here. I want to show that these ideas are, well, either that these ideas are real and they work, or that I'm delusional. Either one is a result which will help in my future development. And that's what I've been doing for several years. And it's come to a point now where I've realized that taking this journey, choosing this rather hard path through this, has led to a slightly different perspective, a slightly different way of looking at the world. And that's what I want to share with you here today. So what I'm going to talk about for the next hour is, what are the challenges that are facing architecture today? What's happening? What is happening in the world of architecture, software architecture, enterprise architecture? And I'm going to talk about architecture as a scientific pursuit and ask some hard questions. Does that even make sense? Is it even a conversation that's worth having? And we'll talk about what the next generation of architectural thinking might look like. And eventually, I'm going to make a call for a more scientific approach to the way we do software architecture. And so this is the third in a series of talks which I've done here at NDC Oslo. Started 2 years ago with a talk on the ideas that I've developed over the last 10 years, which is called residuality theory, and it's the subject of my PhD. And then last year, I challenged the audience to think about, who are you philosophically? Where did you get your ideas from? Why do you see the world the way you see the world? Where did that come from? Are you even aware of where it came from? And as an industry, we definitely are not. And The purpose of this talk is to force you to step back and ask a few questions of yourself and the way that you work as an architect and the way that you practice. And so the first question is, would you describe your design work and your modeling as rigorous? Would we do that? I'm sure some of us would. Some of us would probably tell the truth. What does it mean when we say that something is rigorous? What does that actually mean, to be rigorous? And how do we separate a rigorous approach from one that's not rigorous? How do we define that? How do we get other people to understand that something has a degree of rigor or is missing a degree of rigor? And we're going to ask the question, do the frameworks and the models that we use as architects, do they make our work more or less rigorous? And is this even a conversation we can have? Is software engineering even at the same scientific level as other forms of engineering, what I usually call real engineering? Can we even apply the same way of thinking to these ideas? And is there a way to improve this? And ultimately, we're trying to answer the question, where did the science in computer science go? Something happened along the way. So architecture today, in 2025, is in a bit of a funny place. A lot of developers are rejecting software architecture. They're saying, we don't want architects here, we don't want these lines and boxes, we don't want these people coming in from their ivory tower with their big ideas and their guidelines and their principles. They don't understand the tech. They come in, they make decisions. We have to live with the reality on the ground. It's not uncommon to walk into a large company and find that architecture is being rejected by developers. A lot of architects are angry about this, and I think it's quite understandable. What's even scarier for the architect is the rejection that's coming from the executive level. People are saying, where's all our money going? What are we getting for it? What is architecture or enterprise architecture delivering for this organization? And architecture is getting squeezed from two directions. It's being called out. It's being asked to justify itself. And this is difficult. And the result of this is an identity crisis. Who are we? What are we? What do we deliver? What's the point in us? Very common discussion. If you follow architects or enterprise architects on LinkedIn, you'll see this constant discussion around identity. Who are we? What are we for? What's the point in us? Everyone has different opinions. There are lots of people who say, well, I'm definitely an architect. What I do is architecture, but all the rest of you, I don't know what you're doing. and this goes on, and architecture is stuck in a loop. It just keeps repeating. And this is hard for us to get out of. There are other challenges. There are other things that are happening on the horizon, and I know you probably read the abstract of this talk and thought, here, we can hide for an hour. No one's going to mention Gen AI. I'm sorry, it's only one slide. LLMs, I mean, there's a lot of talk, a lot of speculation. What's going to happen? This room's going to be empty next year, and there's just going to be two agents, one speaking and one listening. Right? And there's a lot of speculation. Nobody knows where this is going to end up. But the one good thing about what's happening is that we are being forced to take a step back and ask questions. What is code? What is software? Does it need people? This is going to force a conversation on architecture. What is it that we're doing? What is it that we bring? What is architecture? And whenever all these vibe-coded systems are running and crashing and burning, then we'll say architecture is the thing that stops them doing that. And then we can rush in and be the heroes. This change in direction, this change in discussion is good for architecture. That was actually ChatGPT. It was heckling me. Did you hear that? It's starting. So the problem we have is this question, what is architecture? What are we doing? It's been decades, and we still can't get a decent definition of what it is that we do. And we have this problem. When it comes to architecture, a lot of us who practice architecture have a belief about this is what architecture is, and that's a belief, something that we've picked up along our journey, our careers. And then On top of what we believe, there's also what we've been told architecture is, which you can be told by any number of groups and organizations and books. This is what architecture is. And then there's what we want to be true, which might not be the same as what we believe, and might not be the same as what we've been told. And there is what is actually true, which is often radically different. And then, on top of that, there is what can be shown to be true about architecture. And when you if you mix a bunch of architects, these 5 discussions are all happening at the same time, and we talk past each other, and it gets confusing. The way to traditionally solve this kind of confused discussion is science and the scientific method that brings us back down to something we can agree on, reduces the noise, brings a bit of rigor to the discussion. Architecture is nothing more than a collection of ideas. And we have, each of us, different ideas about what architecture actually is. We have all kinds of techniques and theories. Each one of us has a little toolbox that makes up our architectural toolbox. And these ideas that exist in our architectural toolbox, they're not subject to scientific review. They're not subject to peer review. Anyone can say anything. And our opinions are often very relative to the experiences that we've had, to the projects that we've worked in, to the cultures that we've worked in. And they're not universal, and they don't travel well. And that doesn't stop us from adopting other people's practices. As long as they put a nice shiny wrapper on it, we'll buy anything. It's very hard to reproduce things. It's very, very difficult for us to take someone else's architectural tools and make them work in a different context. We don't bother proving things. And so architecture is a bit like the Wild West. And it runs on vibes. Everyone thinks vibe coding is this new thing. We've been doing it for a very long time. I'm just going to start heckling me again now. So the question we want to ask then is, can scientific approaches improve software architecture? Can we solve this problem? Is our foundation sufficiently scientific? Does it need to be? Is this even a question? Is it too hard for us? So we're just going to have to skip it. And are we even ready for this conversation? Can we talk about these things without making people angry? This necessarily involves some critical thinking. We have to take a step back, we have to look at our own toolboxes, and we have to say, does this stuff really work? I got taken aside at a conference. And someone said to me, you can't say this about this method or that method. You can't criticize this way of doing things. And I said, why not? And he said, because people love these methods. When you criticize the methods, you hurt their feelings. I thought, oh, okay. And I thought, but people love reading tea leaves as well. My grandmother loved reading tea leaves, and she used to read them, and she would tell your future. And she would say things like, when you grow up, Barry, you're going to have a cat. She was right. And it would have been rude, right? It would have been rude of me to say, Granny, I don't think that your method of reading tea leaves is scientifically sound. That would have been rude and out of place. But if she had said, family, I've decided, based on what I've seen in the tea leaves, to invest all our savings in this particular thing, we would have said, hold on a minute, Granny. This might not be as reliable as you think it is. And so I wouldn't suggest doing architecture by reading tea leaves. And it would be fair enough to criticize someone who was doing architecture by reading tea leaves, unless they were using safe, in which case you might as well just put the kettle on. So the result of all of this is that we have this architecture that runs on vibes, and this creates tensions for us, right? We get carried away by rhetoric, we get carried away by charisma, we believe in tools because someone on the stage said it, because it's in a book. And this leads to disappointment, and it leads to getting back in the hamster wheel and continuously doing the same things over and over again. And that this leads to where we are now, with architecture being questioned and being seen as being all over the place. And so a few years ago, I started talking about these ideas, and I wanted to bring a level of rigor to them. And so I started this PhD program, and walking this tightrope has made me change my ideas about what it is we need to do as architects. A huge thing that I had to do as part of this process, which was difficult, very, very difficult, was to develop experiments. Experiments that show that this idea that I have, this technique, works. And not just that it works once, and not just that it works for me, but that it works in a generalizable way, that it works across the board, that this is a real thing, that I can safely give to other architects and other programmers and say, go with it, this will hold, this will work. And this is a very long journey. Academia means opening up your ideas to an insane level of criticism, which we wouldn't consider acceptable as developers or in the business world. Why do I think that A proves B? Have I read the literature? Is it properly verified? Then you post it to peer review. You get absolutely crushed. You get sent back to the library. Say, you fool, you haven't read all of these books. You haven't understood anything. And it's demoralizing in a good way. The ideas get stronger and stronger and stronger as they're put through this. And this is not something I've ever really witnessed in the business world, writing software for 2.5 decades. These experiments are extremely difficult, they're extremely expensive, and it's hard. And a lot of times you'll feel this, oh, can I not just give up and go back to building stuff? This is so difficult, I'd rather just build something I know that's wrong, put it into production, and just live with whatever happens. That's an easier way to do this. Experimentation is incredibly difficult and incredibly hard. And once I got through this process, I understood why the industry ducks this, why this is so difficult. The shortcut that our industry takes to get around this problem is a magical device called the case study. And the case study is where we take one particular business context, one particular customer, one particular problem, and we solve it using a particular technique, a particular architectural tool. And when I talk about my new ideas, people will often ask me, is there a case study? And I always say, don't ask me that question. Would you believe me if I said there was a case study? Would you believe in the ideas? And they say, yes. I say, you shouldn't. You absolutely shouldn't, just because there's a case study. A case study tells you one thing. This idea worked once, in one place, with the person who invented the idea using it. That's all it tells you. When we work with software projects, they are described as, with this fancy word, idiographic. Idiographic means that this problem that you're trying to solve will only occur once. It will never occur in the same way again. And even if it did, if it happens in the future, things will have changed. There are so many variables moving that nothing can be held still. And so you can never compare two software projects to each other, because there'll be different teams, different countries, different cultures, different stacks, different histories. Everything moves and changes, and so actually comparing two things is incredibly difficult. This leads to the problem that if you have a case study, you cannot claim generalizability. So I can have a case study and I can say, my ideas worked at this customer solving this problem in this year, in this country, in this market. Great, well done. That does not give me license to say that this idea will work if we change any of those variables. It is not generalizable, and this is the big step towards scientific thinking. One of the things in these very complex environments, science gets a bit fuzzy. It's hard to do anything useful here, and one of the things that emerges is a behavior which is quite dangerous, which is called scientism. And scientism is the use of scientific words to make things sound fancy. And this is an incredibly useful tool if you want to sell things to people. Scientism means that I throw in a bunch of sciencey sounding words and it makes everything I do seem more credible. If you want to be taken seriously, add some math equations to whatever it is that you're writing. They don't have to make sense. Right? No one will read them. People will tell you about a method, and they'll say, it's like thermodynamics, or it's like quantum physics. As soon as you hear those two words in connection with software engineering, just run, right? It'll save you money. Get out of there. It's time to put the kettle on again. We have to be careful when we talk about architecture as a science, is that we're not just using these words, these nice thoughts, these nice ideas to make our ideas more credible. This is the first time I've ever used a clicker. I keep going back to change it automatically. It's strange. So another thing that we do, an abuse of science, is that we use science as a rhetorical tool. And I get this a lot. I'll present my new ideas. which are kind of radical, kind of different. And people will come at me with these gotcha questions. And they'll say, do you have empirical evidence for this? And they expect me to say no, because generally in software we don't do this, we don't do this. And I'll say, yes, we do, and they'll get a bit scared. And they say, is it peer reviewed? And I'll say, yes, it is actually peer reviewed, and they'll get a bit more scared. And they say, can we compare it to other methods? And I'll say, yes, we can do all of these things. And they'll say, oh, I was not expecting this. Normally when I ask these three questions, I can knock any idea down in architecture. So this is a bit of a shock. They expect it to be no. And then I flip the script on this and I say, the methods that you use every day when you build software systems, have you seen empirical verification that they work in a generalizable way across projects? And the answer is usually no. Actually, I haven't. I never thought about that. And I ask them, are these ideas that you've put into production that you use, are they peer reviewed? And they'll say no. And they say, but they wouldn't have taught me these ideas if they weren't real. I'm like, okay. And so then I have to ask the question, why are you subjecting a new idea to a kind of scientific grilling that you don't expose your old ideas to? Why are you doing that? And what we've developed is this habit of using science and scientific language to knock other things down, to knock down new ideas, but we have a core set of architectural beliefs in our toolkit, in our toolbox, that we don't dare question. And this is something that is so common in the industry that it sort of has to be lifted up. And then we have to come to the very awkward, very difficult question, what is science? And it turns out this is not easy. We all think we know what science is. We have a vague feeling of what it might be. But what is science? And there's a lot of different interpretations of that. Science is basically saying, how do we know that what we believe is rigorous? And how do we avoid this thing called pseudoscience? We have this enormous failure rate in our industry. We want to do something about it. Can science help? And I asked this question to a bunch of senior people as I was putting this talk together. Do you work in a scientific way? Is your work scientific? And when we ask this question, people tend to think about their everyday work. And they say, well, yes, I form a hypothesis. That's the scientific method. And then I do something that will test that hypothesis and confirm that it works. And if it doesn't work, I'll change my mind and do something else. And therefore, I kind of work scientifically. But it's not our everyday process of developing code that we're talking about. We're talking about the foundational ideas that we use when we develop that code. That is what we're talking about here. And can this process be translated across projects and domains and industries and countries? When we look at our academic history, the history of software engineering, you'll see these names, Parnas and Dijkstra and Constantine and Yeardon, Bohm, Jacopini, Lampart. We should know these names, but too few developers are familiar with these works. If you go back through the 80s and the 70s and the 60s in software engineering, you'll find that there was a scientific core to the way we thought about things. And we've lost contact with that across the years. Very few of us actually actively read academic articles. This is another thing that Gen AI has been really interesting. It's pushed us back to reading academic articles. Dijkstra wrote a paper. Say Dijkstra when you're on stage and pause. Someone will laugh. Dijkstra wrote this paper on the role of scientific thought in 1974. Fascinating paper. It shows kind of how we think and feel about science in this community. He claims that our industry strips scientists of their ability to think scientifically. Dijkstra describes in this article that, look, we get all kinds of people coming into software engineering, biologists, chemists, properly trained scientists. The minute they come in the door and start writing code, they forget their scientific training. They just let it go. They just start hacking. Is the problem us? Dijkstra asks. And this quote from the paper says here, many of them must have felt that scientific thought was a luxury one could afford in the more established disciplines, but not in the intellectual wilderness they now find themselves in. A very important point he makes as well, nothing becomes true because 10,000 people believe it, or false because 10,000 people refuse to do so. Things that we maybe could think about in our industry. On top of all this, architecture, as a dexterous solution to scientific thought, reveals a lot of how we think about the world. He believes that a separation of concerns is scientific thought, that we take just one tiny thing at a time and just work with it, isolate it so that we can understand it. That's one particular way of approaching science. It's called reductionism. But architecture is complex. We're working with complex business systems that don't lend themselves to reductionist techniques. And that's what I talk about in the first video I showed you here on residuality. It's possible in a complex environment where everything's moving to make many claims. It's difficult to disprove them, difficult to prove them. And we end up working with anecdotes rather than data. So when I talk about these things, about architecture as science, I'm actually complaining about the lack of rigor that we have. It's possible to have complexity and rigor, but we have to really work hard to make sure that that happens. So there's a whole bunch of different ways of approaching science and talking about science. One way is something called verificationism. Verificationism is the idea that you can prove that something is absolutely true, absolutely correct. This comes from a school of thought called logical positivism, very closely related to the origins of computer science and people like Alan Turing and John von Neumann. And this is the idea that we can prove a program correct before running it. This is one way that we believe we can approach our problems scientifically. This has become very difficult because of the halting problem, because of Gödel's incompleteness theorem. These formal methods are a result of that. They still exist, they can work, but rarely for entire code bases. A different approach to science is suggested by a guy called Karl Popper. And Popper says that instead of proving that something is true, we prove that it's false. So you take an idea and you just keep trying to break it. And through that trying to break it, you strengthen the idea, you strengthen the theory. And he believes that an idea that can't be falsified, and so he's attacking thinking like Freudian psychoanalysis and say these ideas can't be falsified, therefore they're not science, they're pseudoscience. And he uses this technique to say what's science and what's not science. And he believes that science is the pursuit of falsification. This is useful for finding out what's nonsense and what's not. The problem is if you apply it to most of our architectural methods, very few of them survive because they're not falsifiable, which from Popper's perspective would make software architecture akin to astrology or reading tea leaves. And the problem is that we have these theories. We get theories. We don't really know where they come from. We have theories about how we break up software. We have theories about how we test it. We have theories about how we map that software to the business domain. We don't know where those theories really come from. The problem that these guys who were looking at what science is in the last century saw was that we interpret evidence, we interpret what we see in the real world, our observations, we interpret that through our theories. And the hypotheses that we form aren't really strong because we don't get to see that much in our individual careers. And most of us are too busy to run scientific studies. And it's never really in anyone's financial interest to falsify anything. So the question becomes, where do these theories and where do these ideas come from? How do we develop our idea of what is science, what is scientific, and how we relate that to our work? In 1962, a guy called Thomas Kuhn writes a book that changes how we think about science forever. The book is called The Structure of Scientific Revolutions. And this book is famous because it defines the term paradigm shift. And we'll talk about what that means. So a paradigm is a collection of ideas and thoughts, theories that kind of assembled together, are coherent, and they inform how a particular group of scientists looks at the world and thinks about the world. And Kuhn describes the history of science because he was very interested in how it developed historically. And he says that a paradigm will exist, it will come into creation, it will have some success. And then what will happen is we will start to run some experiments, we'll start to see some observations, some ideas in the real world that kind of make the paradigm shake a little bit. It doesn't work anymore, it can't explain this particular thing. And eventually, there'll be so many anomalies, so many things that the paradigm can't explain that the paradigm experiences a crisis and collapses, and a new idea comes along and a new paradigm emerges from this, which is very, very different. The classic example is the shift from Newtonian physics, which worked very well as a paradigm, but couldn't explain a bunch of things that were happening with Mercury's motion around the sun, things like that. And that gives way eventually to relativity and Einsteinian physics. And Kuhn says that these paradigms, that they are incommensurable. You can't have two at once. They talk about things in such different ways that they can't really understand each other. They use the same word for very, very different things. And he sees history as a shift from paradigm to paradigm to paradigm. And in software, I'm going to make the claim, there's going to be people in the YouTube comments who say, no. But I'm going to make the claim that there have been two major paradigms in the history of software engineering. And that's controversial because if you go to Twitter right now, you'll see that at least two people have claimed a new paradigm since I stood up on the stage here. But two major things that I see in the history of software engineering. The first one I call the computational paradigm. And the computational paradigm kicks off with Alan Turing's uncomputable numbers in 1936, where we start to think about computer science as an extension of mathematics that's provable. That starts to crumble, starts to fall apart. In 1968, a bunch of bigwigs get together in Garmisch, in Germany, at something called the NATO conferences and say, what's wrong with us? Why do we keep screwing this up? Why are we always late when we deliver? And why is what we deliver not what they asked for? And even if it is what they asked for, why doesn't it work? And they all got together and said, well, we suck at this. And they decided that the way forward was to be more like engineers. Software needs to be an engineering discipline. We need to be better at engineering. And that is the start of the second paradigm, which I call the engineering paradigm, where we started to copy other engineers, other engineering disciplines, and bring in their ideas. Right now, today, that engineering paradigm is starting to suffer from major anomalies. And the reason for that is architecture is being dismissed. We're having these failures. We had object-oriented programming. We said this is going to fix everything. Here we are. We said microservices, this will fix everything. Here we are. We're saying Gen AI, that's going to fix everything. We'll see. But it's going to raise new questions. Things are starting to shake around this engineering paradigm. We're starting to ask proper questions about these things. So the paradigm that we're in makes it difficult for us to see anything outside of that paradigm. We can get trapped in a certain way of thinking. But Kuhn has another idea that I think is really fascinating, and he says that before a proper paradigm forms, what happens is something called pre-science. And pre-science is whenever everyone is running around, there's lots of different ideas. No one really knows what's going on. Everyone's arguing. There's no real proof that anything works. We haven't really arrived yet. And it feels like a crisis the entire time. And that sounds familiar. And so I think we are in pre-science as architects. And I think software engineering should happen in a roughly scientific way. But the bigger investigation should be reserved for these ideas that drive our hypotheses, not what we're actually doing. And so an example of how we behave in pre-science is to think about this goat. So if we go back 1,000 years in time to whenever people lived in small villages, they had no science, they had no medicine, they didn't understand the scientific view of the world. And they believed, back in those times, they believed in divinity. They believed that there was a god or gods who steered what happened here on earth. And if a child got sick, they didn't have germ theory, they didn't have medicine, they had no way of explaining why the child was sick. And so they tried to reason, based on their paradigm, why is this child sick? And the one conclusion that they might arrive at is the child is sick because the gods are angry, and the gods want something to die. And then they looked at the goat, and they thought, maybe, if I kill the goat, the gods will be happy that something died today, and they'll leave the child alone. And this is how science happens. You think it happens with people with lab coats and pipettes? No, it happens with people having crazy ideas, doing something and going, ooh. Now, you would imagine that there's no connection between killing the goat and the child being sick. So this is okay. It's safe to experiment like this. The danger is that one day a child got sick, someone killed the goat, and the child got better. And the whole village went, "Ooh, we've figured this out." And the next time a child gets sick, everyone in the goat pen is starting to get real nervous. And sometimes you'll walk into a meeting full of developers and they're all standing up. And you'll think, why are they all standing up in the meeting? What difference does this make to the quality of the code? And the truth is that this is the goat. Once upon a time, a bunch of people stood up in a meeting and everything went well. So now we have to stand up forever. The wall is covered in post-it notes. Those post-it notes are goat's blood that we've smeared all over the walls. This is how we come to knowledge. And this is where we are. As software people, as architects, this is what we're doing. All of this leads to a phenomenon that we need to be aware of. And I call this the Rorschach architect. Every architect who practices is not practicing a shared paradigm. We're not practicing a shared set of beliefs because we haven't arrived there yet because we're in this pre-science. And that means that the set of ideas that form your own personal paradigm as an architect are a function of the projects that you've had the chance to work in, the mentors that you've had, the companies that you've worked for, the things that you've got to build. And this means that we're all very, very, very different as architects. We have completely different ways of looking at the world. It makes it hard for us to communicate with each other. And these kind of ideas will lose credibility if you shine a scientific lens on them. And so the conclusion that I want to come here to today is this. Now, a lot of developers, when they see this kind of fluffy, soft session that doesn't have any code compiling, we have had a bit of ChatGPT going on over here, they'll ask, what's the point in this? What can I do with this? And what you have to do with this is realize that the ability to step back and question your toolbox and question your ideas and question your theories is, for me, a big part of the step from software development, programming, to software architecture. The ability to know what's in your toolbox and how to question and to know that some pieces of it are a little bit shaky is that step to architecture. If you want architecture to move to a more scientific foundation, no one is going to come along and do it for you. We cannot continue to baby bird, like hold our little mouths open and wait for mummy bird to come with a worm. Right? We have to go and get our own worms. One of the things that we're saying in our community, developers are saying, we don't want to be steered by top-down architecture. And the solution to that is not just to get rid of top-down architecture, you're going to have to invent something else that works from the bottom up, and it has to answer the questions that architecture is trying to answer around quality and reliability and the future survival of an architecture. Otherwise, we stay in the hype-focused hamster wheel and we just keep spinning. And occasionally, mummy bird will come and give us a worm. That's a really bad way to mix metaphors. How can a baby bird get a hamster wheel to move? It's a very special kind of bird, the lesser known Irish hamster bird. So, architecture won't become scientific until we push it, until we make it. And you can't replace top-down architecture until something comes from the bottom. So it's up to us. And then you have to ask yourself the questions. Am I a rule follower or am I a thinker? Which one do I want to be? And it's perfectly okay to be either one. If you just want to be told what to do, then you don't ever need to think about what I've talked about here today. Someone else will fix it for you. Although the industry is failing you. The tools they're selling you, the ideas, the architectural frameworks, they are not scientifically verified. And you'll continue in that hamster wheel, flapping your little wings. So we need to be able to scientifically verify the enormous number of tools that are coming at us and to understand what's verified, what's not, and what needs to be done. And thinking scientifically is the demarcation between coding and architecture, for me. That's my own personal opinion. So what you need to do is to constantly apply rigor to the ideas that you're bringing into your team, that you're bringing into your project. Demand more from your methods, falsify them. Be aware that there is a paradigm shift coming. and be aware of scientism and be afraid of that. The engineering paradigm is failing. What AI is trying to do, it's coming at us from this side. AI is coming at us and it's saying, I'm trying to figure out everything that's reproducible, everything that I can automate, everything that I can replace. It's trying to find all those easy bits that can be replicated, that can be borrowed from the past. My work comes at architecture from the other side. It's coming at architecture and it's saying there are all these things that are uncertain, that are undefined, that cannot be defined, that cannot be automated, that cannot be replicated. And these two things are going to squeeze architecture from both sides until we get a more concrete idea of what it is. Both of these things are pushing on the edges of pre-science and saying, what is this? What can we do? These are both steps towards ending that pre-science and figuring out what are we, what is architecture, and what can we do scientifically. And finally, there's one other thinker who's interesting here. He was a student of Karl Popper's and a contemporary of Thomas Kuhn's, and a very entertaining man, and his name was Feyerabend. Feyerabend said, famously, anything goes. When it comes to science, there's no method, there's no structured way of doing things. It's just chaos all the time. And out of that, anywhere within that chaos, a scientific idea can be born. Sounds a lot like architecture. How we get there, how we get to this idea doesn't matter. And the conclusion he draws is that we must dare to think more boldly. Stop accepting whatever gets passed down. And he says that a proliferation of theories makes all the theories that exist stronger. The more theories that we have, the stronger the theories that are there become. And he says, finally, that he was accused of reducing science to anarchy. A lot of people weren't happy. He would have loved what we're doing with software engineering. And I'll leave you with that. If we want architecture to become more scientific, it has to come from the ground up. We have to change how we think about the tools that we use. We have to change how easy we accept tools and ideas within our industry. There is a path to change here. It's hard. It's very, very hard. It's very, very difficult. But the results will be a body of knowledge that can stand up so that the next time the industry tries to replace us with a tool, we'll have answers and we'll have papers and we'll know who we are. Thank you.